Hi class, welcome back to our continuation of the lectures on electrodynamics, and this is the second of the series. Again, our main reference is Introduction to Electrodynamics by David J. Griffiths, and I recommend you to buy this book or get a hold of this book. So for our second lecture, we will start with vector analysis, and we start with vector algebra. So as you can see here in the figure, you have a walk that is 4 miles due north, then you have another walk 3 miles due east. The question is, what will be the final destination after the two successive walks, for example? In this case, the resultant is 5 miles, 5 miles going to the northeast. So if you go back to your origin, you can go from a straight line here, from here going to back to your original point. So in this case, what is the direction of your walk? I mean, in what is the direction? So you can, your final walk. So here you can find the theta. So how do you find the theta there? So tangent theta would just be equal to, this is negative 4 over 3, or theta would just be tangent inverse of negative 4 over 3. So it will give you a negative angle. That means the angle is measured below the horizontal. So the direction is south of east. So you're dealing with vectors here, and vectors are not ordinary numbers. They are composed of a magnitude. A magnitude has a dimension and unit, but as well as a direction. So you have a magnitude and direction for a vector. Of course, you know what scalar is. Example of scalar is mass, 5 kilograms, for example. It doesn't contain any direction, or length of a car with 3 meters, for example. But if you walk, you need a direction. That's a vector. Or if you're measuring a displacement, you need a direction. That's a vector. But if you're just measuring a distance, or say a distance of this path, for example, you're just measuring a distance without direction. But displacement is a straight line coming from your origin to your final destination. That's a straight line, and that has a direction. And if we're dealing with vectors, ordinary numbers, we deal with algebra, and now we're dealing with vectors or quantities with magnitude and direction. We are now dealing with vector algebra. So that's just an example. Displacements are straight line segments joining from one point to another. So you have a direction there and a magnitude. The magnitude is the length of the straight arrow. Actually, vectors are represented by arrow, as you can see in the previous slide. So examples of vectors are velocity, acceleration, force, and momentum. So these quantities have both magnitude and direction. So for example, for velocity, you have 5 meters per second to the west, or if you solve some problems, you translate it to negative 5 meters per second. It's going to the west. Usually going to the west is negative, going to the east is positive, going to the north is positive, going to the south is a negative, going in front of you or going towards you is positive, and going away from you is negative. So that's a convention of direction. And if you're also going to the positive x-axis, you are also in the direction I. And if you're going to the negative x-axis, you're in the direction negative I. For positive y, you have positive j. And if you're going down, that's negative j. Going towards you is positive k, and going away from you is negative k. That's for the z-axis. So what are examples of scalars? For example, are mass, charge. The charge of an electron is the same anywhere. It doesn't need direction. Or the mass of an object is the same everywhere. You don't need to have, or direction is not as important. Density as well as temperature. Usually vectors are represented by bold-faced letters. So you don't usually they represent vectors as A, for example. This is just also equal to a bold-faced letter. And this one here denotes the magnitude of the vector, or just simply A. So when you see a letter with an arrow above, that's a vector. When you have an absolute value of that particular symbol, that's a magnitude of the vector. Or sometimes the vector is written in boldface, or if you put an absolute value, that's a magnitude. So looking at this diagram, you have the length of the arrow here is the magnitude of the vector. So if you have an arrow that is smaller with the same direction, and that is some constant times a vector where k is less than 1, greater than 0. So if you have that, then this is just proportional to each other with your proportionality constant k. This one is also a vector, but as you can see, the direction is on the opposite, exactly opposite as A. So this is the same magnitude, but the direction is opposite. So you have A, and the other one is negative A. So in this case, you have if you look at this, this is your vector A, and this is your vector negative A. They have the same magnitude, but exactly opposite direction. So how do you get the opposite direction of this? So you can just multiply another negative to that. So if you want to get a vector, this is negative of negative A. But this one is, or this vector is just the same as this vector. So therefore your A is equal to negative of A. So it's like ordinary number, but you are changing the direction twice. So it's just like ordinary multiplication, so that's such that you, when you multiply a negative by a negative, gives you positive, or gives you back the original number. So, by the way, the two vectors have different locations. There are other vectors, like if you have a vector like this A, and then you have a vector B here. This is called co-initial vector. Co-initial vector, that means they are coming from the same point. Or if you have this one C, and this one is D, for example, they are going to the same point. They are called coterminous. 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 This is co-initial vectors. If the two vectors are in the same plane, like in a surface tension, you have so many forces in a surface tension, and sometimes the force are randomly directed in a surface tension, like a bubble that is a bubble, flat bubble in a surface tension, and there are so many forces in that surface. Those forces are called coplanar. They're in the same plane. Here you have a vector A is added to vector B. You have a vector A added to a vector B. So you know how to add vectors. You connect the tail of the second vector to the head of the first vector. So this is now your resultant. So C is equal to A plus B. In this case, you have you put the vector B first here, and then later on you added A, and you got the same vector here. You have the same resultant here. So therefore A plus B is equal to B plus A. That means the two vectors are commutative. I mean, the addition of two vectors is commutative. So it doesn't matter which order you're adding. In fact, this can also apply to any number of vectors. No matter how the order is in adding a vector, you interchange the order, you get the same sum. So here, so these are just two vectors. So two vectors are, I mean, the sum of two vectors is a commutative. This one. It's also associative. This means that if you have three vectors, you're adding three vectors. You can add A and B first, then add it with C, or you can add B and C first, then add it with A. So in this now, the next one is you have A minus B. This is just equal to A plus negative B. Because you have A there, and supposedly B is this vector B, and this is now negative B. So you're adding a plus negative of b, which is this one. So what is the sum here? What is the sum, or what is the resultant? So the resultant would be this is a plus negative b. But in this case, the resultant is a difference of two vectors because you're adding a negative. So a minus b is represented by this. Multiplication of vector by a scalar. So here you have a vector a, and then you have another vector here 2a. This means that the magnitude is twice. You are just multiplying a scalar. The direction is preserved. So if this is theta here, this would also be theta. The scalar multiplication is distributive, so you can multiply a to the sum a plus b. This is just equal to a times the vector a plus a times the vector b. So what happens when this is negative? For example, this is negative 1/2. What is negative 1/2 a? Negative 1/2 a would look like this. It's in the opposite direction, and the magnitude is cut by half. So that's it. Then, as a review, we also do that scalar product, or scalar dot product, or just simply scalar product or dot product. And you can only do dot product for two vectors, and the dot product is defined by this formula. The theta is the angle, the smaller angle between A and B. This angle is not the correct one. The theta is the smaller angle between the two vectors. And this angle is formed if you place the two vectors tail to tail. So the tail of A and the tail of B, you put it in the same place and then you measure the angle. Here A dot B is a scalar. It does not have direction. So there's no direction. Remember that. The only vector product between two vectors that you could have direction is the vector product. For the scalar product, there's no direction. And also, this is also equal to b a cosine theta. By the way, the a here, the a and the b here are magnitudes of the two vectors. So your a and b, these are magnitudes, you can interchange that. So what is this b a cosine theta? This is also b dot a. So therefore, your scalar product is also commutative. The commutative means that you can interchange the order. And the scalar product is distributive. So if you dot a vector to a sum of two vectors, then you can dot with B, and you can also dot with C separately. So just like this. The dot product with the sum of vectors is the sum is the sum of the dot products. That's what it means. I'm sorry for for that. So anyway, let's continue. So if you by the way, geometrically, A dot B is the product of A times the projection of B along A. So if you have a vector A, for example, if you have a vector A here, A, and then you have a vector B, for example, here, B, the projection of B along A, this is theta, for example. So you have a projection of B. This is B cosine theta. Sorry, this doesn't have a line, an arrow above. So this is the scalar product. You have A times B. You have A times B cosine theta. The magnitude, just the magnitude. So when the two vectors are parallel, what does it mean? Two vectors are parallel. This means that they are in the same direction. So theta is equal to 0, but cosine 0 is equal to 1. So therefore your cross product, dot product of two parallel vectors is just A dot B equal to the product of the magnitude, this one. So if you're going to dot a vector with itself, here you're getting the dot product of a vector with itself. You get the square of the magnitude. This is just equal to A that A is equal to A times A cosine 0, 0, but this is equal to 1, and you have A square. If A and B are perpendicular, that means theta is equal to 90 and cosine 90 is equal to 0. So everything will be 0. The dot product of two perpendicular vectors is 0. Now here's an example. Let C is equal to A minus B. C is equal to A minus B. This is B, this is A. What is negative B? Negative B is, this is B. So negative B is like, this is negative B. That one. So you can put this, I can put this here. So this is negative b. I can erase this. I can erase it. So here is the sum from the sum of a plus negative of b, or this is equal to a minus b. So c here, this is also equal to c, this one here. So c is equal to a minus b in this figure, that's represented in this figure. So calculate the scalar product or dot product of c with itself. Let's calculate c dot c. What is this? So you can do this. C dot c, you have c is equal to a minus b, and this is also a minus b. Since the dot product is distributive, you can distribute a. You can distribute a here and a there. So that's a dot a and minus a dot b. And then you also distribute b to here and to here also. So this is negative a, negative b dot a. Then you have negative and negative, so this is plus b dot b. But a dot b is equal to b dot a. So therefore you can write your c square. Of course this is equal to c square because it's dotting with itself, is equal to c square is equal to a square plus b square minus 2ab cosine theta. The cosine theta is the angle between a and b. By the way, this is called the law of cosines. Okay, next one is the cross product. The cross product or vector cross product or just vector product of two vectors is a product that has magnitude and direction. The scalar product, the one that we discussed earlier, is a product that has no direction. But this one is entirely different because it has a direction. So A cross B, the symbolism of the cross product is the cross, is equal to AB sine theta. For the scalar product, you have AB cosine theta, but for the cross product, you have AB sine theta. A is again the magnitude of the vector A, and B is the magnitude of vector B, and N here is N is the direction that is determined by your right hand. So if you have A here, and they have a B here, they are separated by angle theta. You put your palm on A, and then you move A, use your right hand, put your palm of the right hand on A, and then move your palm towards B, and your thumb is pointing perpendicular to the plane of A and B. That is your N, the direction of N. So N can be directed to the x-axis, or positive x-axis, or negative y-axis, or negative z-axis. The hat is used to designate unit vectors here. The unit vector is a vector with magnitude of 1, magnitude of 1, but the direction is explicit. It has to be determined, or it has to be like if it's I, J, or K, or theta hat, or R hat, for example. Now we will know what those are later on. What happens when we interchange B and A? So what happens is when we have B cross A, this is equal to negative B A sine theta N. This means that you're putting your palm to B and then you move your palm towards A. So your thumb now faces the opposite direction. So when you have this as N, the direction of this will be now equal to AB sine theta negative N hat. The direction is opposite. So you always have to use your right hand consistently to get the direction of the vector product. Again, vector product has magnitude and direction. The scalar product or the dot product does not have direction. It's purely a number with unit. Look at this. This is the geometric representation of the vector product. By the way, what is this line that I am drawing? This line is just a sine of theta. So this is a trapezoid. This is a trapezoid that is formed by that is subtended by the vectors A and B. So the area of the trapezoid is actually the area of the trapezoid is equal to height times the base, which is equal to the base is B times the height is A sine theta. Area, that's the area. So what is BA sine theta? That's the cross product of two vectors B and A, right? So therefore, if you have two vectors that subtend a trapezoid, the area is the magnitude of the vector product of the two vectors A and B. So that is the meaning of, that is the geometrical interpretation of the cross product. So this one is vector or cross product is distributive. So you can, just like before for the dot product, you can distribute the vector. You can cross it with the sum, and then it's the same as the sum of the cross. So you're familiar of that already. But anyway, this is again, this is negative of B cross A, and this one here is negative of C cross A. This one here. Geometrically, earlier, AB is the area of the parallelogram generated by A and B in figure 1.8 here. That's the area of the... no, I'm sorry, it's not a trapezoid. It's a parallelogram. I'm sorry for that mistake. So when you cross a vector to itself, that would be 0, because the angle between a vector and itself is equal to 0, so sine of 0 is equal to 0. So you cannot cross, I mean, you will not get something if you cross a vector by itself. You can write a vector in component form. We have done this before. So you have a vector that's directed. This is positive x. So in this case, you have for this axis you have x hat. For the direction for this axis is y hat, and for the z axis is z hat. So if you go down here, that's negative z hat. If you go here, that's negative y hat, and if you go at the back, this is negative x hat. That is the Cartesian coordinate system. So arbitrarily, you can write any vector A in this form. You can write it in this form. So AX will be the component along the X, AY will be the component along the Y, AZ is the component along the Z. AX, AY, and AZ could be positive or negative. So that means you can have a component that is negative as well. So let's say, for example, a vector v could be negative x hat plus 4 y hat minus 7 z hat. That's just an example of a vector. So AX, AY, and AZ are the components of A, or the projections of A along the 3 coordinate axis. So vector operations. If you add 2 vectors, you add A and you add B. If you know the components, you just add all the X component, all the Y component, and all the Z components. So if there are many vectors, you can just add all the X components, all the Y, and all the Z components. And if you multiply a vector with a scalar, so here you multiply a vector with a scalar, this is distributive, so you can distribute A to AX, A to AY, and A to AZ. So again, if you have x hat dot x hat, this is just equal to 1 because the magnitude of x hat is just equal to 1, and the angle between x hat and x hat is equal to 0, so cosine of 0 is just equal to 1. So therefore you have x hat, that x hat is just equal to y hat, that y hat is equal to z hat plus times in that z hat, that's just equal to 1. And since x and y are perpendicular, cosine 90 is 0, so you have x dot y is equal to 0, z dot x dot z is equal to 0, and of course y dot z is also equal to 0. So how would you get the dot product of two vectors? So the dot product of two vectors is this one, a dot b, and you have here ax, ay, and az, and then you have bx, by, and bz in the respective direction. So you can, if you expand this, you can distribute a to bx, by, and bz, plus you can also and then you can distribute ay to bx, by, and bz, and then you can also do az to bx, by, and bz. So all you get are nine terms, but only 3 of the terms survive because the x, this has x dot x, and this one has y dot y. They're the only terms that survives. Okay. So the rest of the terms become 0 because that would be x dot y, and x dot y is equal to 0, y dot z is equal to 0, x dot z is equal to 0, so everything is 0. And then you have to calculate the dot product of a vector with itself. So here you have a dot a is just ax, ay, and az. So if you change this with a, then this is just ax plus ay plus az, and that leads to this one. So if you want, this one is equal to a square, and so your a will be this one. For cross product, by the way, take note of this one. For the cross product of unit vectors, if you cross x to x hat to x hat, that is equal to 0, because sine of 0 is equal to 0. You're crossing a vector with itself, so they are 0. But here x dot y, or x cross y, this is equal to z. If you use your right hand rule, if you put x and then move your palm to the y, you get z. And this is, if you interchange the order, you get a negative here. For y cross z, this is also equal to negative z cross y. If you interchange the order, that is x. And then z cross x, that is negative x cross z, and that is equal to y. So again, use your right-handed coordinate system in order to get the correct direction. So if you want to cross two vectors. This is the, so again, you can distribute A to B and so on, no? And then you get this term as your component in the x axis, and this is the component in the y axis and the z axis. You have to take note that there is a direction x here, y, and z. And of course, this expression is actually a determinant that is equivalent to a determinant. So you can write your A cross B as a determinant here. So A cross B is a vector product, and A cross B is a scalar product. Look, it doesn't have x hat, it does not have y hat and z hat. It's purely number. This one you have a direction here. So here's an example. Find the angle between the face diagonals of a cube. So consider a cube of side 1 and place it as shown in figure 1.10 with one corner at the origin. The face diagonals A and B are given by these vectors. So you have A and B. You can easily look at the coordinate system. So A, if this is equal to 1x, 0y, and 1z, and for B you have 0x, 1y, and 1z. So what is the angle between the face diagonals of a cube? So you can get the dot product of A and B. The dot product is just equal to that, using the formula that you can get here, this one. So your A dot B is equal to 1, and A dot B is equal to AB cosine of theta. But A, what is A? A is square root of ax square plus ay square plus az square. So this is equal to 1 square plus 0 square, and this one is 1 square. So 1 plus 0 plus 1 is equal to 2. So A is equal to square root of 2, and B is also the same, square root of 2, if you get the magnitude using this formula. So cosine theta, so this is 2 cosine theta, but AB is equal to 1, so cosine theta is equal to 1/2. So therefore arc cosine of 1/2 is equal to 60 degrees. That is actually, that you can also get that by geometrical process. This one is a diagonal, and this is square root of 2. This one is also square root of 2, and this one is also a diagonal, right? So this is square root of 2. You have an equilateral triangle. An equilateral triangle has angle 60 here and 60 here and also 60 here. So you can also get that by that, but if you're told to do dot product, you have to do dot product. There's a triple product. The triple product is this one is a triple product. A dot B cross C. A dot B cross C is actually the volume of the parallelepiped. This is a parallelepiped. parallelly piped, or you can say parallelly piped, it doesn't matter. So this is a valid operation because look, this one, B cross C, is a vector, and then you are dotting a vector to another vector is valid. That's correct. But this one is wrong. This is wrong. A dot B dot C. This is wrong because this one is a scalar, and if you dot a scalar to a vector would not mean anything. So this is a wrong operation. This one is a correct operation. This one also is wrong, as this is also a wrong operation. A cross B dot C. That is also wrong. Why? Because this is a scalar and you cannot cross a scalar to a vector. So this one is wrong, and also this one is wrong. This is the correct one. So remember, there is also a kind of order in vector product. So this one is correct. The other two are wrong. Evidently, you can also show that this one is correct. They are identical. And also this one. You can prove this by component form. And also this is given by the determinant of this matrix. This is also true. This one. Again, this one is not valid. This one is a vector triple product. This is a correct notation because this is a vector. You're crossing. This is also a vector. For example, you are crossing a vector to another vector. That's valid. So here you have this is called the backup rule. The backup rule, you can remember it. And so you can also write the backup rule for this, which is that one. This one is taken from here. Also, if you want to simplify some expressions, say for example this, you can use the backup also, and you will get this expression. And you can also simplify this into this one. Position, displacement, and separation vectors. Position is very important in electromag because electric field is position dependent. And of course, displacement, if you displace a charge from one point to another, you will create also some disturbance. So the disturbance is very important also because it can produce like magnetic field, for example. So anyway, we define the location of an object in Cartesian coordinates to be x, y, z. So for example, the location of the object is at this point, at this point here. So you have the coordinate system. You always refer to the origin. You have x, y, z. So your r would be x hat, y hat, z hat. And how do you get the magnitude of r? R is just the magnitude of this one. This is just square root of x square plus y square plus z square. The location of an object or a point is a vector quantity. You have r and some direction x hat, y hat, and z hat. The magnitude r is the distance of the point from the origin, and r has that magnitude. And you can get the unit vector r. You can get the unit vector r by dividing vector r with the magnitude of r. So you know this and you know that you can get the unit vector. So how about infinitesimal vector, dl? If you want to move from xyz to x plus dx, y plus dy plus and z plus dz, then you will have a displacement vector dl. dl is equal to dx x hat, dy y hat, and dz z hat. So usually in electrodynamic problems, you will have a source point. A source point is where the electric charge is located. So a source point may be here, a source point may be here, and a field point. A field point is where you measure the electric field or the magnetic field. But the source of that electric field would be, say this is the source, the red one. And this is the field point. There is a difference between the source point and the field point. The distance or the displacement between the source point and the field point. This is called the scripted r. And this is just equal to, this is r minus r hat. This one here. So the magnitude would just be this one, and the unit vector would be this. So in Cartesian coordinates, you will have the scripted r would be like this, and of course the magnitude would be that one, and then the unit vector would be this one here. So this is all for our second lecture. We will continue with the lecture on this topic, again under vector algebra. So I hope you learned something. If you have questions, then you can ask me in our Google Classroom. That's all for today.